Alright guys, today we're going to be talking about water, and we're going to add a new variable. Just know that this is the variable where stuff starts getting smashed and smooshed together. So here's the part where you're going to start needing to know each of those individual variables really well, because we're going to start combining those together to see what happens. So we're going to do a lot of variable chasing today. So a quick review. At this point you should know your atmosphere structure and composition. Do you know the layers? Do you know what it's made of? Do you know how heat energy is different throughout the globe, how that relates to convection, conduction, and radiation? Do you understand how pressure works, that it's caused by gravity, affected by depth, it also is affected by both water and temperature, and that it's the cause of wind? I'm going to give you a moment, so I would say pause the video right here so you can reflect for a second on those three pieces. And because I know you really didn't, we're going to keep going. And then remember that, or you can look at that top of your note packet there. Changes of state, we already know, require the transfer of heat energy. Heat energy either has to go into or out of the water, and in order to make them change state. So if heat energy goes into the water, there's more movement and more disorganization to those molecules. If heat energy is taken out, there's less movement and less organized. And we also found out from our changes of state lab that water or temperature doesn't change during a change of state, because that energy can only be spent, it's sort of like money, it can only be spent on one thing at a time. It can be spent on changing temperature, or it can be spent on changing state. And no matter what, when that energy is going into a system, the molecules are always moving more and spreading out and getting more disorganized. They just don't change their temperature if they're changing state. If energy is coming back out, the molecules are always moving less and getting closer together, but again, if they're changing state, it's not changing temperature. So then you have that triangle diagram there. I would encourage you to fill in the blanks with atmosphere or air, and then water. So for the first arrow at the top there, it says you have got an arrow that goes from liquid to solid. And so in that blank, in order to go from a liquid to solid, the liquid has molecules that are really spread out and disorganized, and the solid has molecules that are tightly packed and organized. They're into crystal form. So that means the energy had to go from the water into the air in order to go from a liquid to a solid. So I would like you guys to see if you can figure out the rest of those arrows. Alright, so if you didn't pause your movie, pause it. And then if you did pause it, fabulous, let's get back going again. So here's your diagram. So on that first one, energy goes from water to the atmosphere. We already figured that one out. The cool thing is each arrow is just the opposite of the last one. So from a solid to a liquid, the energy goes from the atmosphere to the water. If we look at our next arrow here, energy from the atmosphere goes to the water. So in order to go from a liquid to a gas, the molecules have to get more disorganized. So the energy actually has to go from the air, and it has to be absorbed in the liquid in order to make the water molecules move faster. So when we go from a liquid to a gas, or we evaporate, and you can think about this is easy to remember. When things evaporate, they go from a liquid to a gas, it cools you off. And so it's going to do the same thing to the atmosphere. When water evaporates, it cools off the atmosphere. And so then the other way is the exact opposite. As water goes from a gas to a liquid, the energy goes from the water to the atmosphere. And so whenever we form a cloud, it actually makes things warmer. You've probably felt this on a winter morning when you wake up and it's kind of cloudy out, but it feels so warm. That is because those clouds act like a heat blanket, and they heat up the atmosphere. The nights don't get so bitter cold. All right, our next arrow, from a gas to a solid, energy goes from the water to the atmosphere. So in order to go from a gas to a solid, those water molecules really have to slow down a lot, and so they're going to go out of the water and into the atmosphere. And then the exact opposite, from a solid to a gas, energy has to go from the atmosphere to the water in order to make those molecules move more. Now those are really important, especially when we're looking over here, this gas to liquid, liquid to gas. This happens a lot in our atmosphere, and so these play a huge role in that, in weather processes. And that's because that heat energy that's going into and out of, and the water's not changing temperature, is called latent heat. Okay, so, and because it's hidden heat energy. So those blue arrows always mean that that latent heat is released to the atmosphere, and the atmosphere is heated just a little bit. The red arrows represent places where latent heat energy is stored in water and the atmosphere is cooled. And so in those cases, the atmosphere actually acts like a heat energy piggy bank. It stores that heat energy. Okay? So what is that latent heat again? Water has that high specific heat. It can absorb and release energy without changing its temperature. And so this is a physical property, and that means water can absorb and release a lot of heat energy without changing its temperature. And so that becomes hidden heat energy. It's heat energy that doesn't change temperature, doesn't do anything other than kind of get stored in water. And so that's what makes water be able to act like a heat energy piggy bank. So that's going to come into play later, but it's important for us to know now so that we can kind of understand what's going on in our atmosphere. So where does this happen in our atmosphere? Whenever there's condensation or precipitation, that's when energy is released and our atmosphere warms. This is going to come into play for those of you who are interested in that severe storm tornado stuff. Keep in mind that's a key piece right there. And so that's one place where latent heat is released. But then the exact opposite, so flip that around. Evaporation, transpiration, that is when heat energy is stored and the atmosphere is cooled. Anytime that water is evaporated, transpiration just means that's that whole water coming out of the photosynthesis piece. And so that water goes directly into the atmosphere. And so that cools the atmosphere as well. What do we know about water? We already know it can cause pressure differences. We saw how we could crush a can using water vapor. We're going to add two more terms today. We're going to add the vocabulary term relative humidity and capacity. You probably already have a hunch about what relative humidity means, but it's important that we understand how it's so closely related to this capacity piece. So what is capacity? Capacity is the maximum amount of water that air can hold. So think of it like a cup. You can have an 8-ounce cup, you can have a 12-ounce cup, you can have a 20-ounce cup, or like a bottle of water, right? You can have an 8-ounce bottle of water, those little tiny ones. You can have a 12-ounce, the regular size, or you can have a bigger one, the 20-ounce size. But the thing is with capacity, warmer air is a higher capacity. If you think back to what's happening to those molecules in something that's warm, they're moving faster and they're spreading out more. So there's more space between the molecules for water to fit into. And so warmer air has a higher capacity because there's more space between the molecules. So that's that image on the left-hand side of page 2 of your notes there. Likewise, colder air means there's lower capacity because there's less space. So when you start thinking about relative humidity, relative means relative to the capacity. And then humidity, think of what comes to mind. Well, humidity, I think of water. So relative humidity is the ratio of actual water in the air compared to the capacity. That compared to is the important piece. You can't just say it's water vapor in the air because we would just call that water vapor. So relative humidity is relative to the capacity. So that ends up being like a grade. If you got 80 out of 100, that would be a B in our class. And so you can change the relative humidity in two ways. I could change the top value, your top number here, and say, oh, you know, I counted one wrong that I shouldn't have. You got a 90 out of 100. So I could change the amount of water in the air, or I could change the temperature of the air. I could say, you know what, 2 of those questions weren't very good, so we're just going to throw those out. And so that becomes 80 out of 80, and you now get 100. And so you have an image there of a glass of water in your notes on page 3. It just says, how full is the glass to the left? You're going to put a percentage on that you think is accurate. And that number represents the relative humidity of that air mass. Now it is important, look how in that box on your notes you've got changing that should be water in the air. So you can add water to the glass, or you can take it out, or you can change the temperature of the air because changing your temperature changes your capacity. Now, what happens if we get to this situation where we have like 80 over 80? Oh, I forget. Okay, so don't forget, what can change relative humidity? Adding or removing water. This happens with large bodies of water, like large lakes and oceans. Not like the Platte River, not like the Missouri River. It's got to be big like the Great Lakes or oceans. Mountains actually remove water out of the air, and we're going to talk about that. We'll have a whole lab on that one, so just know that mountains remove water from the air. And then changing the temperature, because that changes the capacity. For us here in Nebraska, that's going to be the most likely source of a change in relative humidity. So we're going to see daily changes in relative humidity because we're changing the temperature. And so here's a little graph that kind of shows you what happens. This is 100% relative humidity. So you notice it doesn't take very much water in grams to fill up air that's at 0 degrees. But by the time we get up to 50 degrees Celsius, it takes a lot of water and air to fill it up. And this would be a 50% line. What's 50% of that value? And so the colder you get, the less difference there is between those two, and the warmer you get, there's more difference between those two. All right, so what exactly is 100% relative humidity? We call that point 100% relative humidity saturation. That's the point where if I added a drop of water, it would overflow, or it would be too much for that air to hold, or if I cooled it just even a partial degree, it would be too much for that water to hold, or for that air to hold. So if air is cooled or if water is added, that water is going to overflow out of the air. And so if it's cooled, and we tend to reach that point of 100% relative humidity by cooling air, we call that the dew point temperature. And so the dew point temperature is what the meteorologists will use, because that helps communicate how much water's in the air. Higher dew points mean you have really moist air, and lower dew points mean you have really dry air. And so if you had a parcel of air where it's like 70 degrees Fahrenheit, 20 degrees Celsius, and 50% relative humidity, if you cooled that air down to 50 degrees Fahrenheit or 10 degrees Celsius, you'd hit that dew point temperature, and that would be 100% relative humidity at that point. If you cool it any farther, or you add even a tiny amount of water, what ends up happening is you get condensation. Okay, so air cooled past that dew point is going to condense because you're pouring that water that's full just absolutely to the brim into a smaller cup. The extra water that won't fit is going to come out of the cup. In our case, if we were looking at an actual cup, it would spill, but we don't have a giant cup in the atmosphere. What we see instead are clouds, or we would see fog, or we would see dew or frost. And so if you get to that point of condensation, you get those results. So, what does this mean? Well, we have to first think of our temperature and pressure. Pressure is going to be by far your go-to start point. So if you're like, okay, so I need to apply this, what does that do to pressure? Always start with temperature and pressure. So I know that hot stuff, you would say, rises, and cold stuff sinks. Okay? So what happens to the temperature as warm air rises? As warm air rises, so on your notes on page 4, you've got a little thing that says ground, and right above that says hot air. So draw an arrow up to that box. So as warm air rises, the temperature decreases. So where you see temperature, right, the word decreases. Well, what does decreasing temperature do to our capacity? That makes it a smaller cup. It decreases. So if I pour water from a big cup into a little cup, it looks more full. And so that's going to make the relative humidity increase. And if I increase that relative humidity enough, so if I decrease that capacity far enough, I'm going to get things like clouds and rain. Likewise, the opposite happens to cold air. To cold air. So cold air, if I know that cold air sinks, as cold air sinks, I'm going to get my temperature increasing. If my temperature increases, then my capacity increases. If my capacity increases, my relative humidity decreases. If my relative humidity decreases, I'm going to get sunny, clear weather as cold air sinks. Okay, so this is a good spot to pause. If you don't have your diagram on page 4 filled out, I'm going to give you, this would be a good place to pause and get that taken care of. And then get out your air masses and fronts notes, the ones from where we have the water tank with the red and blue water. So pause this here till you have that out. All right, so the question on that back of that air masses and fronts page, it said, where are the clouds and why do they form there? And it gave you an image that looked like this, and there you can see where I placed the cloud. So why does it go there? It goes just behind the cold front edge. First off, we know this is the cold air because it goes underneath this part, and the warm air is going to go on top, so hot stuff rises and cold stuff sinks. So we know this is the cold stuff, we know this is the warm stuff. So the clouds are going to form right behind that cold front edge. And so because that cold air pushes into the warm air, you got to remember this air right here used to be down here, right? So as this air goes up, it cools off. And as it cools off, its capacity decreases and it reaches that dew point and it forms a cloud. If it gets cooled enough, or if there's enough water in the air, it's going to rain. Just because you have a cloud doesn't mean you always have rain. So keep that in mind. Like I'm looking out the window right now and I see blue sky and fluffy clouds and it's not raining. Just because we have a cloud doesn't mean it's necessarily going to rain. All right, now I know you have page 5 left in your notes there. We're going to save that for adiabatic temperature changes. That's going to be a whole sort of different YouTube, and we'll take care of that on your next one. All right, thank you.